Have you ever wondered how a computer can understand that Paris is to France what Tokyo is to Japan? I mean, for decades, that was a huge problem for AI. Computers are great at calculating, sure, but they can't actually comprehend language. Well, today, we're going to demystify a technique that totally changed the game, not with complex grammar rules, but with surprisingly simple math. Let's dig in.
To you and me, this is an obvious question, right? But for a computer, the words king and queen are just a bunch of letters. It has no idea about royalty or gender or power. So, how in the world do you teach it that these two words are deeply connected? Well, cracking this puzzle is the key to everything, and it's exactly what Word2vec was designed to do.
So, the secret sauce is this incredible concept called word embedding. Here's the idea. Instead of seeing words as just text, we give every single word its own unique set of coordinates, kind of like a point on a giant multidimensional map. This coordinate is a long list of numbers called a vector. You can think of it as the word's unique address in this massive meaning space. And these numbers aren't random at all. They're very carefully calculated to place words with similar meanings really close to each other.
Okay, and this is where things get truly mind-blowing. Once words are just points on a map, vectors, you can start doing math with them. Yeah, math with words. The most famous example is this one. If you take the vector for king, subtract the vector for man, and then add the vector for woman, where do you end up? Unbelievably, you land right next to the vector for queen. It's a language analogy solved with basic arithmetic. It's just wild.
But how? How on earth does a computer figure out what all those numbers should be? How does it build that incredible map of meaning in the first place? All right, let's dive into our first section and really get to the core principle behind this word math.
The whole secret, the big idea, is context. The model basically reads a huge chunk of the internet, billions of sentences, and it learns one simple rule. A word is defined by the company it keeps. So words that show up in similar sentences, surrounded by similar neighbors, end up getting assigned similar vectors. It's kind of like if you see two people always hanging out at the same coffee shops and libraries, you'd probably guess they have similar interests. Same idea, but for words.
And what's so cool is that the model doesn't just learn one type of relationship. Just by looking at the context, it figures out that walk and ran are related because they're both actions. It learns that but and however are related by their function in a sentence. And it even figures out that Berlin and Germany are related as a capital city and a country. All of this just from looking at word patterns. No dictionary, no rules, just patterns.
Okay, so we know the model learns from context. That's the what. But what about the how? What's the actual process look like? In Section 2, we're going to look at the really clever mechanics of how it actually learns all this stuff.
You know what's funny is that this super high-tech AI concept is actually based on a surprisingly old idea from linguistics. It's called the distributional hypothesis. Way back in 1957, a linguist named J.R. Firth said, "You shall know a word by the company it keeps." Word2vec is basically that exact idea, just turned into code.
So to put this idea into practice, the creators of Word2vec came up with two really clever and kind of competing strategies. You can think of them as two different ways of playing the same language game, each with its own special trick for learning from a word's context.
All right, here's the breakdown. The first one is called Continuous Bag of Words, or CBOW for short, and it's basically playing a fill-in-the-blank game. You give it the sentence, the quick brown blank jumps, and its one job is to predict the missing word, fox. Simple enough? But the second approach, skipgram, totally flips the game on its head. You give it the word fox, and it has to predict its likely neighbors, words like quick, brown, and jumps.
And you can really see the difference here. On the left, you've got CBOW. It takes all those context words, the surrounding words, and uses them to zero in on the missing target word in the middle. But on the right, skipgram does the complete opposite. It starts with a center word and works its way outward, trying to predict the words that are probably its neighbors. They're really just two sides of the same coin, each one trying to figure out that relationship between a word and its friends.
So why have two different models? Well, you can think of it like the classic story of the tortoise and the hare. CBOW is the hare. It's way faster to train, especially on huge amounts of text. But skipgram, that's our tortoise. It's slower, for sure, but it's way more careful. It does a much better job of figuring out the meaning of rare or unusual words, and that can be absolutely crucial for getting the nuances right. Now, this wasn't just some clever idea in a research paper. This was a massive breakthrough that literally changed the entire field of AI. So in Section 3, let's look at where Word2vec came from and why it made such a huge splash.
And like most big breakthroughs, this didn't just appear out of nowhere. The basic idea of word vectors had been floating around since the 80s, but honestly, the methods were just painfully slow and inefficient. The game really changed around 2010 when a researcher named Tomasz Mikhailov started using more modern neural networks for this problem. All that work finally paid off in 2013 with the landmark release of Word2vec.
And he wasn't working alone. This was a true team effort at Google, with some absolute legends of the field. You've got names on here like Jeff Dean and Ilya Sutskever, who are still some of the biggest names in AI today. And together, they released a tool that would completely change how we all work with language.
So what made it so revolutionary? Well, the older methods were kind of like creating a basic dictionary. They could tell you which words often appeared near each other, but that's about it. Word2vec was like creating a thesaurus and an encyclopedia all rolled into one. It was so much more efficient to train, and it captured all these subtle relationships between words that older models just completely missed. It was a huge leap.
Which brings us to our final section, the lasting legacy of this incredible idea. Because even now, more than a decade later, which is like a century in AI years, its influence is absolutely everywhere.
You can draw a perfectly straight evolutionary line from Word2vec to the most powerful AIs we use every single day. Just a year after Word2vec, the team expanded the idea from single words to entire documents with something called doc2vec. And that fundamental concept, learning these representations from context, became a core building block for the massive transformer models like BERT and GPT that power everything from your Google searches to ChatGPT.
Now look, it's true that by today's standards, the original Word2vec algorithm is, well, it's dated. More powerful, way more complex models have taken its place, but that doesn't make it any less important. In fact, the fundamental principle behind it, that meaning comes from context, is maybe more relevant now than it ever has been.
So, while the technology itself has evolved like crazy, the central lesson from Word2vec is the big takeaway here. It proved that meaning isn't something you just define in a dictionary, it's something you derive from context. That simple but incredibly powerful idea that you can understand a word by the company it keeps, well, that's the bedrock that nearly all of modern language AI is built on.